program. This level looks like a major milestone, considering memory needs to it. And actually, we only have one more intermediate level before we get a working computer. Well, still two. I haven't even opened the program yet. But... okay, that looks like RAM. The instruction input component has been removed. I see. It has been replaced by a program component. Every tick, the counter... what? Oh, every tick used the counter to load the next instruction from the program's memory. Use the counter. Oh, I do remember unlocking a counter. Is this it? So... yeah, I guess a program is a piece of memory. Expected. Yeah. Byte RAM. I think these are exactly the same component. Are they not? Oh, I can even move the program around. No. That broke the circuit. I'm just wondering if... oh, right, this field is unlimited. Just wondering if they're the same. Yeah, they're the same. So a program is a byte RAM. Delete not working again. So yeah, program is just a piece of RAM, and from it I load by an address, and an address is just the offset for which nth bit of RAM I want. Cool. You must use the counter component you unlocked earlier for this level. Sure. Okay. But wait. It's kind of too simple. This was just my... I just had an instruction here, and now I'm just replacing the instruction with a counter to a program. By the way, what are the inputs? Increment, overwrite. Does it tick on its own? It ticks on its own. Wait. That's it? That's the level. The level was just add a counter. Basically, we already had a program at the start. They provided us with a program, and all I needed to do was to add a counter to it. Okay, well, then I think I'd like to take the time to go back to my previous design, to this part. I don't intend to do much about it, but I kind of shied away from playing around with these switches. I'm not sure if they are necessary at all. Especially considering the disable enable pin over here. So I think I might at least be able to remove this one. I'll just pipe this into the disable pin. But also, this is probably going to be more of a complaint rather than an actual actionable step I can take. But I wanted to mention these huge buses. Again, calling them buses. So these things basically, right? These 8 lines, or I have 7 right now. It seems really, really wasteful to have such a huge contraption only to pipe 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, and 6 to 6. Well, 7 to 7. Right? This line, every line here, only has one destination, you know? So, I mean, at least this much space is being wasted. Which I guess I can just remove these the way I just did. And say that this is my setup. But still, it seems rather wasteful. Right, and I don't have the buses for no reason. I think this is just a neat setup, which is more extensible if I want to take the signal from here, for example, or if at some point I want to go down. So yeah, I wonder if there's a better way to do this, but I cannot come up with anything. Okay, now that that's out of the way, let's take a look at these switches as promised. So, okay, first assumption, or first, what's the word? Hypothesis? First consideration is, do I need this switch? Let's just try removing it, I guess, and let's see. Let's see how this goes. Yep, this just works. Because I assume that's because when this thing is disabled, even though we're piping something into here all the time, when it's disabled, it's no problem that I'm spouting out an output. But this switch I think I do need. Although, does this thing output a signal when disabled? It doesn't. Okay, this means that I don't need this switch either. And I only need to use this enable disable line. Okay, that simplifies my setup quite a bit, actually. Cool, that's cool. And I think I might wanna just wire these a bit nicer. Something along these lines, I guess, will do for now. Okay, let's check. Yeah, this is still correct. Cool. I have a program now. I still feel like my ALU is limited. It performs very few operations, which of course I can derive more operations from it by applying it multiple times, but I feel like I could do more with it. Okay, well, just like before, I'm not gonna touch this too much anymore, and we'll proceed with the next level. Was it immediate or intermediate? Immediate, okay, immediate values. We need a way to directly move numbers from our program into registers. What? So you're telling me I load the instruction into registers? We need a way for this. We use the immediate mode when the two highest bits are off. When in immediate mode, the whole byte is interpreted as a number. Which whole byte? This whole byte, the byte read from the program? The whole byte is interpreted as a number that we save into register 0. So I guess that's a way to have constants in my program. Right? Compile time constants. Though no compilation is happening here. This means we can save any value between 0 and 63. What? Whole byte is interpreted as a number that we save into register 0. This means we can save any value between 0 and 63. I do not understand this. Why does this mean we can save? A byte has range between 0 and 255. If we interpret the whole byte as a number and we save it into register 0, then why don't we save the whole byte and it's 255? Any value between 0 and 63. What? This makes no sense. The whole byte is interpreted as a number. Well, I mean, I can already see, I think, what they mean, but this is not exactly... This is not Again, I do not like the wording of this. Right? So we do need to use the two. Well, we already used them in here. These two bits. Why did that update? Okay. So we do need to use these two bits to determine the mode. And then, since we already know that these two bits have to be set, we only have these bits free. And they are indeed in the range of 0 to 63. So I guess that's what's meant. I don't remember what immediate... Oh, I do remember because it's written right here. It's written on the output. Okay, so this is gonna be my immediate mode. Why does it get updated all the time? Weird. Just disable everything. No? No. Okay, so this is our immediate mode, and we need to use it to save, to register... Well, we need to save to register 3, right? Or to register 0. So I feel like I just pipe this into the save pin of register 0. And my value does... Wait, no, my value actually doesn't get piped into the regular... Again, I'm gonna call this bus, for lack of a better word, into here. So, I don't want to do this. Yeah, that will be a short circuit and everything and all. But I can, for example, use a switch. Oh. Let's take a switch. Okay, so I kind of want to... Oh no. This is annoying. Okay, I'll wire this up and I'll be back. Right, so I'm not done yet, but I just moved some stuff around. Added some more colors. So this is gonna be my immediate mode, and I want my immediate mode to enable a switch that will... Ah, this is annoying. I want to flip a switch. Is it not possible to flip things in real schematics? Because I imagine this is fairly similar to what's actually happening. Right, well, of course, we're making a lot of simplifications, as we've learned in some of the previous levels, especially from the comments. I believe there is, like, notation, so this not and this or are really notationally correct. Though I don't know how much this actually influences the layout of what will be printed, or how do you even fabricate these things? I don't know what I'm saying. Okay, so this is my immediate mode, and if I'm in immediate mode, then my bus value is just the value. And I also need to use it to OR with my save line, just like so, just like here. Okay, I want more space. Well, good thing we're all nice and orthogonal. Cool. Yeah, forgot to select these guys. Them as well. Okay, I have a lot more space now. So this OR... I'm not happy with this OR. But I don't know how to make it nicer. Well, whatever. Let's see here. So I want I guess let's do this. I don't want any color for this because this is a complex instruction. And now I need... well... is this maybe better than having the... Yeah, I think this might be better than having the green go down. No. Not sure how much space I'm gonna need in here still. Okay, cool. I think that's it, actually. Yeah. I wonder what this program is, because this is clearly some kind of program. Maybe it does something cool. And there's gonna be a big reveal when we can actually interpret the results of this. But of course, right now it's completely unreadable. Just a bunch of bytes. Can I, by the way? Yeah, you can. A lot of negatives here. A lot of negatives. So we have our bit 7 enabled quite often, which suggests a lot of copy and condition instructions. Okay. Alright. Alright. I think that's it for this one. This looks fine. This is not too bad. Let's double check. Register values. Onwards. Wow. Just like that? Turing Complete. Until this point... oh. We get the jump. Until this point, all possible programs have been confined by running in order, byte by byte. Before, only code could influence memory. Now memory must influence code. With the addition of conditional logics, our computer can run any algorithm and calculate anything calculable. The final thing we need to add is a mechanism for changing the program counter through instructions when certain conditions are met. Well, good thing we have an override value. Cool. The final thing we need to write instructions when certain conditions are met. When the two largest bits, largest you call them, not most significant, that's curious, are in the condition mode. We are in condition mode. In condition mode, the value register 3 is compared... okay. Is it a coincidence that register 3 is the output of my ALU? I think not. I think not. If the condition is true, we override the counter to the value in register 0. Sure. Man, this gives me assembly flashbacks. This gives me really strong assembly flashbacks. I've never actually dealt with assembly up close, but I've had to analyze some programs in which assembly was used inline, you know, like inline assembly in C. And this really speaks to me, but I don't remember what the instruction was. Okay, if the condition is true, compare it against the conditions defined by the lowest... wait, what? The largest is compared against the conditions defined by this lowest 3 bits in the instruction. We override the counter to value in register 0. Conditionally changing the counter means we can skip instructions based on conditions or have instructions run in a loop. Sure. Oh. Wait. Wait, I already have this conditional. Oh, this is why it leads to here. I see. Well, we already have our optimized implementation. So this looks exactly the same as that, which means we can use our lovely compact cond component. These conditions correspond to the condition component that right, that was saved in the component factory. Well, see, just reading everything and then going back to stuff and commenting on stuff is also unfun. So I don't want to interrupt these manuals with some comments of my own sometimes, but it does end up in some weird situations like this. Okay, so it's not entirely clear to me what I need to do. So I understand condition and I understand register 3, but what do I do with the result again? Right, I need a boolean, or rather I get a boolean. What do I do with it? If the condition is true, we override the counter to value in register 0. I see. Okay, so if this is true, then take register 0 and overwrite. Otherwise, do nothing. Conditionally changing the counter means we can skip instructions. Based on conditions or have instructions? Sure. Okay, cool. Cool. I need a reminder of how my conditions were implemented. Okay, so I am ignoring all bits other than the first 3, which means I'm probably safe to pipe just basically this into it, and it's fine. Input result. Let's check. Let's play around with the instruction. Okay, condition. Never, always. Sure, this is fine. Okay, that seems pretty simple still. So question is, where do I put this thing? Where do I need the result? So the result is true. If the result is true, then I need to override this guy with this guy. This I can always just load. It's no problem. So basically I need to use this condition to have... Yeah, so I just need it piped into here, pretty much, right? I assume the 8-bit counter... Is this a thing I implemented myself? I'm curious, I don't remember. Counter. What is this? Okay. Yeah, 8-bit register. Yeah, and I count. And then I can overwrite. What happens if I pipe an input into it? I decided to go back and take a look at the actual source as opposed to experimenting with it. What happens if I don't have my overwrite enabled, but still am piping an input? Yeah, so it's fine. It's just going to be absorbed by the mux. Cool. So I don't need to worry about what I pipe in. This can constantly be, so basically I can have a constant connection from here to here, you know, like so. And then this guy just decides whether I do or don't. Condition is this. And the value to compare is this. wait, no, it's this. Well, that's no problem. This is simple, right? I can, you know, I can actually just do it right now. Yep, we're done. This is solved. But the real challenge here is how do I manage these wires? Okay. I don't wanna have it messy like this. So how about we move the counter down, or maybe even put it in line with these guys. You know, this is kind of my control flow. This is my memory. But the condition, this is my operation. Is a condition an operation or a control flow? I mean, I'd say conditions are like control flow. So let's say I have it piped like so. This guy just goes back into the program. And then, oops. And then I need my overwrite value taken from here. Goodness, this is... How do I take it? No, I cannot take it up. Oh well. Oh well. There's not much I can do. There's not all that much I can do. And now that we have our overwrite value, again, I need to pipe. Okay, let's move the decider off the main line, just the way I did with the byte splitter. Which, by the way, I should mention, I think last video I kind of watched a portion of my last video. In the part where I counted the gates in here, I actually counted the byte splitters as gates or as components. But my understanding, my actual proper understanding, is that these byte splitters are not components and they're just syntactic sugar. I guess this game's equivalent of syntactic sugar for 8-bit lines. Right, so this counts as 0. This is nothing. This doesn't exist. I could just as well have 8 things going here instead of the blue wire, and then it would behave exactly the same. But it's just the byte splitter is here to save me some tedious work. I think the exact expression was tedious busy work. Okay, all right. So let's move this over like so. Here's our control flow, and the input to this guy. Wait, right, this is wrong. The input to this guy is register 3, but the input to that guy is register 0. Perfect. I think this is right. This is wrong. Next, what's wrong? What am I missing? Let's reset. Let's do take 1. Next tick, the counter value will be 0. It should be 1. Condition. Oh, wait. I also need to bar my condition from being executed if we are not in condition mode. Of course, I completely forgot about condition mode. Sure. It's no problem. remove this as well. Oh, come on. Why is this a problem? Seriously? Are you seeing this? Why? I guess there's invisible pins in there, which I am just not... haven't been told about yet. Okay. We'll find out later. Sure, so... Still, I think my condition... yeah, this... I will always execute my condition, and instead I will bar the overwrite by this decision. So let's use a switch, a single bit switch, like so, and then we can pipe. Wait, do I need to negate this? Condition, if true, then do. No, I don't need to negate this. Cool. Okay. What's gonna be my condition color? Condition feels white to me, but I've already kind of set white as my output line color. So let's use gray. Oops. Keybind. Cool. So this is our condition line. Let's check. It is time for celebration. Commence celebration. Yes, you did it. No comma. I thought you were just this odd-looking hairless ape creature, but you actually built a real computer. Amazing. How is that elephant doing, I wonder? And also, how is that 8-armed sea creature doing? And am I not getting eaten anymore? Is my question to you, Mr. Alien Person. Close. We got the Steam achievement, and we unlocked program as our own component, as well as a manual entry. Turing Complete. Certain computers, like simple calculators, are limited in the algorithms they can perform. They cannot perform any calculation that requires looping or recursing an arbitrary amount of times. Well, okay, I'm not gonna go into it. Technically, machines without looping or recursion can only deal with combinatorial logic. Huh. Turing Complete machines, on the other hand, are as powerful as it is possible to be. A Turing Complete machine may have a slow CPU, but it is powerful in the sense that there is no computable algorithm it can't perform. Yeah, computable is the key word here. Okay. I guess we're Turing Complete. How are we Turing Complete? We are pretty Turing Complete. I feel pretty Turing Complete. But I can't do anything with this. I can't write an actual program that will do anything. I have my output and I have my input, but... Cool. Good thing there's more levels to come. Do I optimize this now? I don't. And in fact, I think that'll be it for me for now. Just because I feel like this is a milestone on which I should stop and reflect. So perhaps a slightly shorter video, but I think it's fine. Cool. Turing Complete. Roll credits.